Today we will be talking of algorithms for clipping polygons. In the last class we had seen methods of clipping straight lines and curves as sequence of straight lines. We had seen that if we have a clipping window and a straight line crossing that window, how we can clip it at the clipping edge and get the portion which is inside the window. Okay, the line could be either like this or like this or totally inside or totally invisible. We had seen different cases and we had seen methods of deciding what portion of the lies inside the polygon and what portion lies outside. Today we will see a related problem, that is how to clip a polygon. Now a polygon is a sequence of edges, but we cannot directly use the same method, because if we use the same method, this polygon will be clipped into a set of line segments which would be this line segment, this portion and so on. It won't be clipped into a closed region. Initially the polygon was a closed region. Once we do the clipping, we still want to retain that this is a polygon and we want to retain this as a closed region. The reason is simple, that if we want to do any polygon filling, or if this polygon is a solid area, by solid area I mean a region which is filled inside, either by hatching or by all the pixels inside being lit by polygon filling algorithms. If it is solid area, or we want to process this polygon later for further clipping or for other applications, we want to retain this as a closed area. If we need it to be a closed area, then finally this polygon should be clipped into a sequence of edges including these edges. Okay, only then it will become a closed polygon. Okay, for clipping a polygon and then finally getting a closed polygon from it, the basic technique would be if this is a clipping window and we have a polygon crossing it like this. As I said, finally we want this clipped polygon which is okay. We clip this polygon first with respect to one edge. Let's say this is edge 1, then with respect to the second edge, then with respect to the third edge, and so on. Okay, we clip it with respect to each of these 4 edges separately. When we clip it with respect to the first edge E1, we will get a polygon which would look like this. Okay, then we will clip it with respect to the edge E2 and this will be clipped onto this portion, and then we will clip with respect to edge E3 and E4. Okay, and when we are clipping with respect to any single edge, we have to keep in mind that initially we will input a sequence of vertices like this. Okay, the output should also be a sequence of vertices something like this. Okay, so a sequence of vertices would represent that this is a closed region or a closed polygon. Okay, the input is a closed polygon, the output should also be a closed polygon. That is the prime thing that has to be kept in mind. Okay, the way we would do it is, if we have any pair of points, let's say pi and pi plus 1, where one point is inside the clipping region, the other point is outside, then the intersection of the line pi plus 1 with respect to the clipping edge has to be included in the output list. Okay, so this point, which is the intersection I, this will be included in the output list. On the other hand, if we have a case like this, where this is, let's say, Pj and this is Pj plus 1, mind you, right now I am clipping with respect to the clipping edge E1. So Pj is outside and Pj plus 1 is inside. In this case, this intersection point I has to be included in the output list, and Pj plus 1 has to be included in the output. Okay, because Pj plus 1 will also be inside the clipping region. Okay, because the clipping edge is the edge E1. Okay. While in this case, Pi plus 1, where Pi is inside and Pi plus 1 is outside, Pi plus 1 will not be included in the output list, only Pi and the intersection point I would be included. Okay. On the other hand, if we have a case like this point and this point, both the points are outside. In that case, we don't have to bother. Neither of these 2 points would be included in the output list. Okay. If we have both the points on the correct side or on the within the clipping region, for example, in this case, Pi and this intersection point I, when the clipping edge is my edge E2, then obviously both these points will be retained in the output list. Is that okay? So corresponding to that, we will get 4 cases. Let's say this is the clipping edge, and this, let's say, the correct side of the clipping edge, this is the wrong side of the clipping edge. We have a Pi and Pi plus 1. This is one simple case. The second case is when both the points are on the wrong side of the clipping edge. One case is a case like this, and the fourth case, a case like this. In both the cases, this is the intersection point and this is the intersection point. Okay. The input was P1, P2 till Pn, and we will start with the point P1 and keep processing each of these points one by one. Okay. So let us say we have already decided about the point Pi and we want to decide about the point Pi plus 1. In the first case, Pi plus 1 would be included in the output list, Q with the appropriate number. Okay, will be included as, let's say, Qj. In this case, Pi is already included in the output list, so intersection point I would be included as Qj. Okay. In this case, where Pi and Pi plus 1 both are on the wrong side, no action would be taken. Okay. The point Pi plus 1 will be ignored. Okay. And in this case, we have already processed the point Pi which was on the wrong side, so at that time we would have ignored the point Pi. But now I as well as Pi plus 1, both these points have to be included in the output list. So this I and pi plus 1 would be included as qj and qj plus 1. Okay. So this way, if you have a polygon, we'll start with the first point P1, go through all the points, clip this with respect to one clipping edge and get a list of points Q1, Q2, so on till Qm. Then take this list, clip it with respect to the second clipping edge, get another output, then clip that with respect to the third clipping edge, and then with respect to the fourth clipping edge. Okay, so this process will be repeated 4 times, once with respect to each edge. Okay, and this algorithm is referred to as Sutherland-Hodgman algorithm. Any questions with respect to this Sutherland-Hodgman algorithm? In all these clipping algorithms, one very important thing is finding out this intersection point. Okay, seems to be a very trivial exercise. You only need to find the intersection between two straight lines. Okay, but maybe you can take that as an exercise and try to write a code which will find out the intersection point between two straight lines. It's not as trivial as it sounds. Okay, well, you have to take care of cases when the two lines are parallel. Okay.
So
Again?
intersection point.
Yes.
Suppose
Again?
the intersection point is in decimals, so it is going to truncate that.
Yeah. We'll round it off.
So the effect of rounding off is not that.
See, the effect of that is not going to be critical because as it is, this line is going to be displayed as a sequence of pixels. So you want to cut the line only at a pixel which is displayed. Okay. So whatever intersection point you find out, you round it off. That would be a point to be displayed. So there will be no problem. There's a question from that side?
You won't run into a problem of being parallel because if it is parallel, then one point cannot be inside and the other point outside.
Okay. Think of a case like this. This is your clipping window. Okay, and your clipping polygon is something like this. Okay, what happens in a case like this? This is your clipping polygon. Yeah, but when you are trying to find out the intersection point, at that time you shouldn't get overflows. You shouldn't get a division by 0 if you are trying to find out the intersection point between these two lines. Between this as a clipping edge and this as the edge.
So in this case also you wouldn't find the intersection because either this whole line will be inside or this whole line will be outside.
How do you decide that you will find the intersection or not? You have looked at this point which is your point pi.
Yeah.
Now you have got a point pi plus 1.
Yeah.
How do you decide whether you want to find the intersection or not find the intersection?
One is inside, one is outside.
Pi you have already processed and you have included pi in the output list. Okay, now you have got a point pi plus 1. Okay, you know the coordinates of pi and you know the coordinates of pi plus 1. Now you have to decide whether to find the intersection or not to find the intersection. Okay, so you look at pi plus 1. Okay, pi you've already included in the output list, which is, let's say, Qj. Now Pi plus 1, you have to decide whether this is to be included or not. Now this point, what you are saying is you will always be treated as a point inside and you will not try to find the intersection at all. That might not happen. In some cases you might say that this point is just outside because of errors in deciding out the difference might be very small.
Say in the worst case it is at the line. Even in that case, if we decide it is inside.
If it is just outside the line,
If it is
maybe
in terms of integers, the points are given in integers.
We can have a simple check for it, a separate check for it.
you have to have a separate check for it.
Both points for x, same x coordinate, and that coincides with the one of the clipping edge.
No.
Keep that line as it is.
What kind of check that you can think of, but you have to have some kind of a check so that such cases are taken care of. In fact, in all these problems, whether it is clipping or whether it is even polygon filling or any algorithm, you find that such cases always give a lot of problem. You have to take care of such, let's say, seemingly trivial cases, and that is what makes the code sometimes quite complex. Okay, in fact, if you try to write a clipping algorithm, you will find situations where such cases come up. Okay, and you have to explicitly take care of such situations. In fact, even in the line clipping, okay, a simple line clipping case where with respect to this clipping window, you want to clip this line. Okay, what happens if this line is like this? Okay, and you want to clip it against, let's say this edge, the top edge. If you try to find out the intersection points, you will get absurd results. Okay, and mind you, intersection point has to be found out efficiently. Okay, efficiency is of time concern. Okay, so the number of methods for finding out the intersection points which are available. Okay, what I suggest is you can go through the book. You'll find some methods for finding out the intersection points. Okay, but in all those methods, you have to be careful about such cases. Okay, if you try to find out the intersection point of this edge or this line with the top clipping edge, as I said, you can possibly get NDO overflows. Okay, division errors. So all such cases have to be taken care of. Yeah. Okay, I just coming to that. So far we have been talking of rectangular windows. Okay. Now a window need not always be rectangular. Whenever we have a rectangular clipping window, it is referred to as a standard clipping window. A clipping window can be of any arbitrary shape. Okay, let's say my clipping window can be a polygon like this. Okay, or it can be even a concave polygon like this. Okay, the algorithm that we have discussed so far, we have been talking of a standard clipping window. Strictly speaking, yes, why not? But that will make the clipping much more complex. Okay, typically a curved edge can always be split up as a sequence of edges. Okay, so even if you have a curved edge in a clipping window like this, we can talk of it as a polygonal clipping window. Okay, now this is a convex clipping window, this is a concave clipping window. The some algorithms which are suitable for convex boundaries only. Okay, for example, the Sutherland-Hodgman algorithm. We are clipping this polygon first with respect to one edge, then with respect to a second, and so on. Okay, if we follow this algorithm for a convex clipping polygon like this, we first clip with respect to this edge, then with respect to this edge, then with respect to this edge, and so on. We'll still get the same result. We'll still get the correct result. Okay, but if we follow it with respect to this concave clipping volume, clipping area, we will not get correct results. Okay, the reason is quite straightforward. Let's say if I have a polygon like this, and I first clip with respect to this edge, and I'll take a portion which would look something like this, this way, and so on. Then I clip with respect to this edge. When I'm clipping with respect to this edge, my polygon will get changed to this. Then I'll clip with respect to this edge. Okay, and my polygon will get changed to this. Now obviously this is not the correct result. So if you have any concavity in a clipping region, then we need different algorithms or different ways of handling this. Okay, so if you have a convex clipping algorithm, a convex clipping region, the Sutherland-Hodgman algorithm is good enough. Okay, but if we have concave clipping areas, then we need to modify this algorithm, or we need some other ways of handling the. Okay, we won't go into details of a concave clipping area. I'll just very briefly tell you how it can be handled. The details maybe you can look up elsewhere. Let's say if we have a concave clipping area like this, what we'll have to do is we'll have to split it up into a set of convex areas. Okay, and set of convex areas would be something like this. So we'll get one clipping area like this and a second clipping area like this. Then we'll clip the polygon with respect to both the areas separately. Okay, and the result of clipping this polygon will not be one polygon but two separate polygons. One which is inside this polygon and the other which is inside this polygon. Okay, so if we have any concave clipping area, we'll have to split that into a set of convex areas. And again, you can think of algorithms for doing that.
How do we decide it is concave?
How do we decide whether it is concave? How do you define a concave area?
No, how do you decide it for a machine? What is the algo? Because for determining its concavity.
For determining the concavity, if you have any polygon like this, okay, or you have a polygon like this, okay, you want to decide whether a particular polygon is convex or concave. How do you define concavity? Anyone? One at a time, please. Yeah. So line joining any 2 points should remain inside that totally. Then it is convex. Okay. How do you check it algorithmically? Draw a line between all the vertices. Okay. So let's say if you have n vertices, you have to draw lines between all the n vertices. That means you have to draw n square lines.
Between two adjacent vertices.
Two adjacent vertices will always be inside. Alternate vertices. Even then you will have n square edges. So you have to check for n square lines where they are totally inside. Yeah, NC2, that is out of n square. Any other way? Anyone? It's quite simple. Even then you will have about n squared by 2 edges. Okay. between alternate vertices. What you're not realizing, let's say I'm taking this point. Let's say I'm taking this point. I check it with all the other points, all the lines are inside. But it's still a concave polygon. That won't work. Okay? Alternate vertices. See, let's say I'm taking this edge. I have to decide whether this edge is completely inside the polygon or not. How do I decide that?
One point within it. Just decide one point within it.
Not one point. I have to decide whether the complete edge is inside the polygon or not.
No, but if it is, if one point is outside, all the points will be outside. There will be at least one edge for which all the points will be outside.
Okay, but I'm just saying how much is the total time required to check that it is not order of n, because for each edge deciding whether even one point is inside or outside,
Again, please you are drawing all the lines.
that would mean that will take order of n time, right? So total time required for checking whether it is a concave polygon will become n squared again. Okay, in this case n squared is the number of edges, the time required will become n cube. Okay, this is still n squared time you are using, even simpler than that. How do I decide whether any polygon is convex at a particular point or not?
Yeah,
So
the angle made by the
If the interior angle is less than 180, so we can keep finding out the interior angle at all the endpoints. Okay, we are given a sequence of P1, P2 till Pn. We can find out the interior angle at each of these points. If at any point we find that the interior angle is greater than 180, that means it has to be a concave polygon. Okay, so this way we can decide whether a particular polygon is concave. But then let's say if you have a clipping polygon which is shaped like this, you have to split it into a sequence of, or into a set of convex polygons. Okay, we'll have to do something like this, and maybe something like this. Okay, 1, 2, 3, 4. We'll get four convex polygons for this case. Okay, how do we do that? We can again think of algorithms. We won't go into that right now.
How do we make sure that both the edges are giving the angle which is we actually need? Matlab, it might give the
Think of that, right? Okay, what he is basically saying is, when you're finding out the angle here, you can find out the angle, but how do you know which is interior and which is exterior? Okay, you can find out the angle between two lines. But how do you know which angle is interior and which angle is exterior? Okay, give it some thought. It's straightforward. Okay, so the basic point is that if we have a concave clipping area, then our clipping algorithm becomes much more complex. Okay, another thing related to clipping, which we'll come back to later on, is what is referred to as 3D clipping. Okay, or three-dimensional clipping. That means if you have three-dimensional lines or three-dimensional entities and we want to clip them with respect to a clipping volume, not an area, how do we do that? Okay, what are the situations in which this comes and how it is tackled? We'll come back to it later on when we talk of three-dimensional 3D graphics. Okay, but any question that you have on 2D clipping, okay, either polygonal clipping or clipping of line segments or curves, we can take it up right now. Okay, then we introduce another topic, and that is transformations. and right now again we will be talking of 2D transformations. We will go on to 3D very soon. Okay. Now, what do we mean by transformations? We have already seen that if we have the world coordinate system, WCS, I am using a short form for world coordinate system. In this world coordinate system, we can take a finite window, and then this portion of the world coordinates is transformed onto the screen coordinates. Okay, and on this screen coordinates, we take a viewport, okay, and this portion of the window is then mapped onto the viewport, okay, after necessary clipping and so on. If you have any point here, let us say a point xy, that will be transformed onto a point here, that will be, let us say, xs ys. Okay, so a particular point here will get mapped onto a point xs ys. Now this is what is referred to as a viewing transformation. Okay. In viewing transformation, the point in the world coordinate system is transformed into a point on the viewport in the screen coordinate system. Okay, and the transformations involved in that are referred to as viewing transformations. Okay, typically, let us say in the world coordinate system, this is my 0 0, and this point is my x lower, y lower, and this point is x upper and y upper. When I transform it onto the screen coordinate system, this point xl yl should be transformed as into a 0 0. Okay, so this point will become a 0 0, and if this upper corner is xy, then this will get transformed into xy. Okay, so this is one case where points in one coordinate system are transformed onto a second set of points. Okay, there can be other situations where, let us say, if we have some entity, either a line segment or a rectangle or any such entity, and we want to either rotate it or reflect it about a particular axis. If we reflect this about this axis, about this plane, let us say, this line segment will get transformed into a line segment like this. Okay, a point on this, let us say a point here xy, will get transformed into a point x prime y prime. Okay, if I know the equation of this line, let us say y is equal to mx plus c, how do I find x prime y prime for a given xy? Okay, the point xy is being transformed onto a point x prime y prime. Okay, so this is another case where transformations are important. Okay, the transformation need not just be reflections, they can be either reflection or rotation or scaling or any such case. Okay, we will see each of these transformations one by one and we will see how it can be done
With the help of matrices.
with the help of matrices. Okay, the first simple case is of translation. How do we define translation? A point xy will be transformed onto, let's say, x plus tx and y plus ty. Okay, so if I write it let's say mathematically, this will become x prime will be equal to x plus tx, y prime will be equal to y plus ty. Okay, this is simple translation. Any point is translated by a vector. Okay, if we have a line segment like this, this will be translated by a vector onto a location like this. Okay, this is translation by a vector given by tx dy. Okay, and that can be captured simply by addition of x and y, tx and ty in the x and the y coordinates. Okay. Then we talk of rotation. We have a point xy and we want to rotate about origin O and by an angle theta. Okay. This is my origin O and we have a point here. We want to rotate this point about the origin by an angle of theta. Okay, theta is defined to be positive in the counterclockwise direction. This is the point xy, this is the point x prime y. What will be the value of x prime and y prime? Anyone? How much will be x prime?
X cos theta minus y sin theta.
X cos theta minus y sin theta, and y prime
X sin theta
Plus X cos.
x sin theta plus y cos theta. Is that okay? Anyone having any doubts about this? Okay. Now this can be written in the matrix form like this. I am writing x prime y prime as a row vector x prime y prime. This is equal to the row vector xy multiplied by this 2 by 2 matrix. Okay, so xy multiplied by cos theta minus sin theta will give us this first equation. Xy multiplied by sin theta cos theta will give us the second equation. Okay, so these two equations can be written in a matrix form like this, and this transformation will capture a rotation about the origin by an angle of theta. Okay, the third case is scaling. Okay, and how do we define scaling? If we have a point xy and we want to scale it by, let's say, sx in the x direction and sy in the y direction, this xy will get transformed to a point which will be given by Sx multiplied by x comma Sy multiplied by y. Okay, the x coordinate will get multiplied by Sx, the y coordinate will get multiplied by Sy. And in terms of matrix notation, we will say x prime y prime will be equal to xy multiplied by Sx0 0 Sy. Okay, so what would happen in a case like this is, if we have a rectangle and you scale it, then this will maybe get modified to something like this. If we are scaling it by a factor of 2 in the x direction and a factor of 2 in the y direction, this rectangle will get modified to a location like this. Okay, this is basically magnifying by a factor of Sx and Sy in the x and y directions. Okay, so this is how scaling can be captured. Now, by using a combination of these three transformations, we can get any other type of transformation. By using combination of translation, rotation and scaling, we will be able to get reflections, we will be able to get rotation about an arbitrary point. Okay, we can rotate, we need not always rotate about origin, we can rotate it about an arbitrary point here. Okay, but using a combination of these three, we will be able to get any arbitrary transformation. Okay, we will see how we can combine the transformations and how by combining different transformations we can get arbitrary transformations. We will see that in the next class.